Hello everyone. Last class we introduced you to the concept of interdiffusion, and basically also I told that what is the driving force for the interdiffusion. It is basically the chemical potential gradient which drives the interdiffusion process. So today I will show you some examples, several micrographs also to give you more feel of how the interdiffusion zone looks like. And we will talk about the factors which affect the phase growth, and we will see how the microstructure or the phases develop in the interdiffusion zone. So let us start. So as I said, basically interdiffusion happens when you place two metals in contact. So typically diffusion couple setup, or when you are doing an interdiffusion experiment, a fixture is looks something like this. You have these two metals A and B for which you want to measure the interdiffusion. You put them in a fixture which is made of stainless steel, and so that the metal A and the stainless steel, there is no diffusion occurring. We also put a spacer, which is typically a high melting element like molybdenum or tungsten sometime. So these are these are thin sheets as spacers that are put, and this entire assembly is sealed in a quartz tube which is evacuated and purged with argon, so as to ensure that there is no oxidation that happens during the annealing process. So once the annealing has done, so once the interdiffusion takes place, predominantly you can have two types of phases or two types of structures developed in the interdiffusion zone. One, you can have a solid solution formation in the interdiffusion zone. So basically you will have in that case a profile something like this. What it means is that the composition of A and B are continuously varying in the diffusion couple. There is like no jump or so that happens in here. So this is the solid solution, and therefore it will proceed something like this. The another possibility is that you have the intermediate phases or the intermetallic phases being developed in the interdiffusion zone. So you have, for example, here you have two types of phases. In the next lecture, I will also discuss that there are two types of phases that are commonly found. One are the line compounds or the phases with very narrow homogeneity range, and another which is having a wider homogeneity range, something like NiAl or FeAl and so on. So for such phases which are narrow phases, you basically get almost a horizontal line. For the phases which are the wide intermediate phases or the wide homogeneity range, you can have a certain gradients which are present. So what you notice is that there is a jump in the composition. Let's say if you take the composition of B, there is a jump from here to P1. Similarly, from P2 to B, there is a jump. So these jumps are indicative of the fact that you have an intermediate phases forming and not really the solid solutions here. You can have a mixture of both in the interdiffusion zone as well. So it's not necessary that only solid solution or only the intermetallic phase has to form. You can have a combination of them as well. So now we will slowly go ahead and take specifically the some of the factors that govern the phase growth in the interdiffusion zone. So I will just tell you before that I'll show you some micrographs of the solid solution development and also the phase growth development. Remember one thing, that in both the cases you notice that there is a lot of variation of composition. So even if you have a solid solution, there is a composition difference in the interdiffusion zone. Similarly, when you have phase growth, there is a lot of difference of composition in the interdiffusion zone. So if you recollect your Fick's laws, where we wrote first that dou C by dou T is equal to d dou square C by dou x square, let's say the second law of Fick's in the simplest form, there the assumption was that D is independent of the concentration. But very clearly it should be now intuitive to you that when there is so much of change in composition, and here you also have different phases, so now the diffusivity cannot be assumed to be constant. So if now you cannot take the d out of this derivative. So earlier you remember this was the part where the first law was used, and this was the part which came from the equation of continuity. So here you had you have dou c d times dou c by dou x. So if the d is independent of concentration, you can take it out and the equation is simple, the life is simple, the solutions are more straightforward. But the moment the d is not constant, the d is dependent on the concentration, then you cannot take this d out here, and therefore now the equation becomes something like this. It becomes d tilde, this symbol is called as tilde. So this d tilde, which is the interdiffusion coefficient, times dou square c by dou x square, plus a non-linear term which is d by dc of d tilde into dou c by dou x whole square. So this particular term makes this equation now not an ordinary linear equation, but it makes it non-linear, and therefore the analytical solutions are not so straightforward. How do we solve this interdiffusion equations is not going to be the subject in this course, but there is another NPTEL course titled Multi-Component Diffusion by Professor Kaustubh Kulkarni from IIT Kanpur. It's available on NPTEL. You can read more about how to solve these equations mathematically, what are the techniques to solve. You can refer to that lecture, or of course you can also refer to the reference books that I have mentioned in the beginning of the course. So now let us move ahead and see some examples. So this is the micrograph I wanted to show you, which indicates the solid solution formation. So you have a titanium iron alloy here, a titanium chromium alloy here, and you see that there is no very distinct contrast present here except for the alloy contrast itself. But in the interdiffusion zone, it is very difficult for you to see any contrast, which itself is a slight indication, a first-hand indication that there is a solid solution formation. And if you look at the micrograph, you see that there is a continuous variation of the composition that occurs. So this is the chromium composition, this is an iron composition, this is taken from this particular reference. Let me show you example of phase growth. So you can see immediately the phase growth when an intermetallic phase grows, a very distinct contrast can be seen, as opposed to what you saw in the previous micrograph, where it is not a very distinct contrast in the interdiffusion zone. But when an intermetallic phase grows, then you can have a very distinct contrast. So this is an example of cobalt tin diffusion couple, where a cobalt SN3 intermetallic phase is grown on the interdiffusion. So let me ask you one question. We will try to answer this later. But for example, if you make a diffusion couple of A and B, okay, so just let me mark it that this is here is A and this is B. If we make a diffusion couple of A and B at this and anneal them at this temperature T, the phase diagram is schematically shown here. In the interdiffusion zone, what are the phases, what are the layers you expect to see? Will it be alpha plus beta, beta plus gamma, or it will be alpha, beta, gamma, alpha, beta, beta plus gamma, or the fourth option alpha plus beta, beta plus gamma, gamma? Can you intuitively guess which one of the layers you may be seeing? When I say alpha plus beta, I mean that a mixture of alpha plus beta. So we will answer this question towards the end of this lecture. So the first feature, let me tell you now certain features of the phase growth that happens in the interdiffusion zone. The first being that in a binary diffusion couple, you will have only single phase regions growing. Okay, so let me show you this example. For example, this is a nickel gallium phase diagram, and this is the diffusion couple. So you will see that here there is only a single phase region which is growing, which is Ni3 Ga7. So you have only single phase regions. So there are these two phase regions that exist at this temperature, but in the interdiffusion zone you have only single phase region developed. Then another example I will show you. For example, you have zinc silver. Let's say the diffusion couple was made and annealed at 673 Kelvin. You have all these single phase region, dual phase regions, and so on. But in the interdiffusion zone here in the micrograph, you can see that you have only epsilon, you have gamma, you have beta phase, but not any phase mixture. So you will not have a layer which has both epsilon plus gamma. You have only the regions where epsilon is there, gamma is there, beta is there. So you don't have a mixture of phases developed in the interdiffusion zone in a binary diffusion couple. Another feature is that, so in the previous two examples I showed you, that only the single phase regions will be visible in a binary diffusion couple. There will be no mixture. Now the next question is, if there are multiple single phase regions, will all of them be visible in the binary diffusion couple? The answer is no. Let me show you some examples related to that. For example, you have this titanium aluminum diffusion couple, in which you have several single phase region. You have a solid solution of titanium Ti3Al, TiAl, TiAl3, and so on. But now the question is, will all the single phase regions be visible? No. When you see the diffusion couple that was analyzed at 823 Kelvin after annealing for 96 hours, you have only TiAl3 in the reaction layer. So in the interdiffusion zone, you have only TiAl3 being developed. And this tells us that all the single phase regions will need not be visible. Now let me show you in the subsequent slide what are some of the factors on which the phase growth depends on. So the one very easy to understand is the temperature. Temperature controls the phase type of phases that can grow. For example, if you see a tungsten zirconium phase diagram, this is a schematic shown here, and you have this intermetallic phase, you have two phase regions, and so on. So if we see the micrographs of the diffusion couple which was made between tungsten and zirconium and annealed at different temperatures, you see at 1300 degrees centigrade you have the W2ZR. You notice the thickness of these phases. So although the phase is same here because you have only one intermetallic phase, although you have certain solid solution regions, but you see the thickness of the phase changes as you change the temperature, because that is because as you go higher and higher in temperature, the diffusivity is enhanced, and therefore the phases can grow to a larger thickness in the interdiffusion zone. So another example is from a aluminum copper system. So you see here for instance that here this is aluminum, this is copper, and here is the interdiffusion zone which is developed. And you can see here that this ABCD refers to AlTCu, AlCu, Al2Cu3, and Al4Cu9. The extent of each of these phases changes significantly as you change the temperatures. So for example, if you notice the thickness of D, it is much less at 480, but becomes significantly high at the 540 degree centigrade. Okay, so like that the temperature plays an important role in affecting the phase growth. The second factor is time. If you allow more time at a given temperature, the interdiffusion zone, the phases can develop, their thickness may be increased. In some cases, you may have different phases evolving as well. So just to illustrate, if you take the same example of aluminum copper, so at 540 degrees centigrade for different times, you can again see the thickness of each of the phases changes significantly as the time of the annealing is increased. So time is one important factor which controls the phase growth. Another instance is the same TiEl that was shown previously. You see here that the thickness of Ti3El layer after 5 hours versus the thickness after 96 hours. So this is significantly high. So time is therefore another important factor which influences the phase growth. Then phase growth for different end members. So what I mean here is, let me show you. For example, if you consider a cobalt tin phase diagram, so if you have a diffusion couple of cobalt and tin, what you see is a cobalt SN3 phase developed in the interdiffusion zone. Whereas if you make a diffusion couple of cobalt and cobalt SN3, what you will have is a cobalt SN2 phase growing. So if you change the end members, the phases that grow in the interdiffusion zone will also change. Their thicknesses will be different, the phase itself will be different. This is another example of tungsten silicon system. If you take tungsten and silicon diffusion couple, then actually the phase that grows here is WSI2, and if you make a diffusion couple between W and WSI2, then the phase that grows in the interdiffusion is W5SI3. So these are the schematics that are adapted from this paper. For the original micrographs, you can refer this particular paper. So in the ternary diffusion couple, what I mean by ternary diffusion couple and binary diffusion couple, just let me reiterate quickly in case. So when I say binary diffusion couple, it is only 2 elements are there, tungsten and silicon. 3 that is ternary diffusion couple, that means there can be 3 elements involved. So now the question is that we saw that in the binary diffusion couple only the single phase regions grow. By the way, I hope you have noticed that even in here you will see only single phase regions. In all other examples, you see that whenever there is a binary diffusion couple, only the single phase regions are growing. So can we see a phase mixture in a ternary diffusion couple? Let us see an example. So you have a diffusion couple between aluminum one side, and here it is gold palladium, and here you see that you have a phase mixture, a region of phase mixture that is developed here, and similarly you have so here, let me come back to this example in a minute, but here you see there is a phase mixture. There are 2 phases, 2 types of contrast that you can clearly see in this region. So there are single phase regions as well, but there are the mixture of phases that also grow. And again you see this alpha is the solid solution here, so you can have a mixture of solid solution, intermetallics and so on developing in the interdiffusion zone. But it is not necessary. See again, let me tell you that in a ternary diffusion couple you can have a phase mixture growing, but it is not necessary that in every diffusion couple which is ternary diffusion couple you will see a phase mixture. For example, here is an example of gold, silver and aluminum diffusion couple where you have only single phase regions in the interdiffusion zone. So although it's a ternary diffusion couple, only single phase regions are developed. So let us try to answer this question now, that what is the phase, what are the phases that you will see in the diffusion couple which is annealed at this temperature T. And from the previous discussion, it is clear that the the phase mixtures will not grow in a binary diffusion couple. So the correct answer is alpha, beta and gamma. Again, this is, you can expect to see, it is not necessary that alpha, beta and gamma, all the 3 should grow. It depends on the actual kinetics of each of these phases, but you will not see a phase mixture. Now the question is, why is it so? Why is that that you do not see interdiffusion zone in a binary diffusion couple? You only see a single phase region. So the answer here can be understood from the Gibbs phase rule. So we saw that Gibbs phase rule is F plus P is equal to C plus 1, which is the condensed phase rule. Now here, since we are doing the diffusion annealing at the constant temperature also, so it becomes F plus P is equal to C, and you have at least 1 degree of freedom utilized, because you see that you are varying, the composition is varying in a diffusion couple. Okay, so we already saw that in the interdiffusion zone the composition is varying. So therefore 1 degree of freedom is utilized already. So what you have is the maximum phases that can grow is C minus 1. So the maximum phases that can be in equilibrium in the interdiffusion zone is equal to C minus 1. So for a binary diffusion couple, C is equal to 2. And therefore the P max is equal to 1. And therefore you see, and this is true, we have seen in the actual examples of the micrographs as well, that only single phase layers grow in the case of binary diffusion couple. So hope that is clear to you. If there are certain doubts still, you can post the questions in the forum. We'll try to elaborate further on this. And next week or the next lecture, we will take some more examples of how to draw the composition profiles in the interdiffusion zone when we know the phases that are being developed. So thank you, and we'll continue in the next lecture.